Hi, I am Aish and I am going to talk about the design of the CPU and how this can be translated to a HDL code. This diagram is the proposed design for the CPU architecture in which I am going to explain the HDL code of the CPU. In the following diagram, the CPU consists of several logic gates such as the ALU, A register, D register, PC, and the multiplexer. Since we have built most of these logic gates from the previous task, in this task it will be easier to implement the CPU HDL code with them. The first step to implement is to derive API of the CPU. API specifies the chip name, the input and output pins, and the function of the CPU. And now let's start off with an abstraction of this chip by hiding all the logic gates in the diagram, so that we can easily identify the input and output pins of the CPU. Now, as we can see, there are three inputs coming into the CPU from different sources of the computer. These inputs are the instruction INM and reset. The instruction input is from the instruction memory. The instruction can either be an A instruction or an C instruction. On the other hand, NM is the value of the currently selected data memory register and is the value that CPU uses to perform its operations. This diagram was used to implement the hack computer in one of the tasks that we have done previously. Here it can be seen that the CPU takes its instruction input from the instruction memory and also takes the value of the selected data memory register as one of its inputs. The reset input in, is a value that tells whether we bring the CPU back to its initial state or, to be specific, to start the operation of the CPU all over again. Furthermore, along with the inputs, CPU has several outputs that are connected to the instruction memory and the data memory as well. These outputs are called as write-m, address-m, out-m, and PC or the program counter. To the given CPU architecture, we can see that the ALU gives an output that is written to the data memory. In order to do so, the ALU must specify a few things first. The content that the CPU is going to write into the data memory, which is stored in the outm. Second, the address of the write operation in the data memory basically. This is where we want to put the content in the data memory. Lastly, the output that allows CPU to write the content to the data memory, write m. The the program counter holds the address of next instruction, which will be then fetched, decoded, and executed by the CPU in the next cycle. Now that we have identified the inputs and outputs of the CPU architecture, we can now implement the code of the CPU. This slide shows the chip name and the names of its input and output pins. Since we are implementing the CPU chip, the chip name that we are going to write for this code is CPU, as shown in this code. The input pins of CPU consist of 16-bit INM, 16-bit instruction, and reset. On the other hand, the out pins of the CPU will consist of 16-bit outm, writem, 15-bit address, and 15-bit PC. The input and output in this header section of the CPU do correspond the design that was shown and discussed in the previous slide. Now here we have three different gates: NOT gate and MUX16. These gates allow the CPU to function and perform specific operations. Firstly, there are two types of instructions coming into the CPU from the instruction memory. These instructions are the A instruction and the C instructions. A instruction has a symbolic syntax of add value. This value can either be a number, that is a decimal, non-negative number, or a symbol. If the value of A instruction is a number, then the instruction will set the contents of A register to the specified value in the instruction. If the value of the A instruction is a symbol, then the instruction will set the contents of A register to the value that the symbol points to, and this value will not be the actual value in that memory register. On the other hand, C instruction has a symbolic syntax of dist equal to compare and jump. This instruction performs a computation on the CPU, which is stored into a destination register or a memory location. It can also tell us the CPU to jump to another instruction memory memory address that is pointed by the value or the symbol. In the first lines, we can see that the NOT gate is used to tell whether an instruction coming into the CPU from the instruction memory is an A instruction. But first, the CPU decodes the 16 bits instruction into an opcode and 15-bit value. If opcode is 0, the instruction is an A instruction. Whereas if the opcode is 1, the instruction is a C instruction. For instance, if the instruction coming into the CPU from the instruction memory is an A instruction, the CPU takes the specified 15-bit value and stores the value into the A register. However, as you can see in the diagram that was taken from the CPU architecture, the A register can be fed by either the instruction input or the ALU output. If it is a C instruction, it performs the computation in the ALU and the ALU output is fed to a register. We use the AND gate to determine that the instruction is C instruction. A 16-bit multiplexer is also used to select whether the instruction or the ALU output is stored into the register A. Next, we have an OR gate. The load bit in the A in the A register would be 1 if either the A instruction or the ALU output is fed to A. On the other hand, the A register is used to store the value that is fed into the A register. It takes in the output A region from the multiplexer and the output load A from the OR gate as its inputs. The output A out then generates the value that is currently stored inside the register. Then mux16 takes in the output of the A register and the value that is currently selected in the data memory register in M. This will select which one to output, A or M. Either A or M will then be used as an input in ALU depending on the 12-bit instruction value. The AND gate is employed to determine whether the ALU output is loaded to the D register. The D register is then implemented to load and store the value of D register from the ALU. The ALU computes a function on two inputs, which in this case would be the value that is stored in the D register and the value of either of the A or M registers, and then generates output. It consists of input control bits, which are indicators of which function is computed on the two inputs to produce output, whereas the output control bits determine the properties of the result. The first two or 16 and the AND gate helps us to set the ALU outputs in order to successfully write on the data. The next few lines determine the address of write operations. The program counter is a register which contains the address of the instruction to be fetched next. In this part of the CPU HDL code, the load bit of the PC is determined by the jump bits and the ALU outputs. Basically, these lines of code determines jump conditions and check the ALU output to see if the conditions are met. If the instruction of is C instruction and the conditions are met, the program counter is loaded with value that will ask the CPU to jump to the specified value or symbol. If the PC is not loaded, then PC is incremented.